Okay. And we are live. Hello, everyone. I'm Maura Pintor, and I'm a PhD student at the Machine Learning Security Laboratory at the ProLab in University of Cagliari. And today we are starting our first seminar series on machine learning security, and we have our first host, who is David Stutz, and he's presenting his ICCV paper on relating adversarially robust generalization to flat minima. Just a few things before we start. First, this seminar will be recorded and also live streamed on YouTube. And you can ask questions. If you are in a Zoom call, you can raise your hand and ask questions directly to David. Also, during the presentation, he encourages to stop him and ask questions. Otherwise, at the end of the call of the presentation, you can raise your hand, and I will allow you to ask questions. Or if you don't want to do so, you can also write questions on the chat or on the YouTube stream, and then we will ask the questions directly to David at the end. And finally, let's also, if you want to receive updates on the following events to this seminar series, then subscribe either to Twitter, to our account, which is displayed on the slide, or also you can follow us on Eventbrite, because we will post the following events there. And let me thank also who helped organizing these seminars, which just started. And I'll leave the floor to Catherine now, so she can present our first speaker.
Hello, nice to meet you, everyone. So I'm introducing David. He's a researcher focusing on obtaining robust deep neural networks. But let me start a little bit with his bio. So he wrote his master thesis at the Planck Institute for Intelligent Systems, supervised by Andreas Geiger. And he completed an exchange program with Georgia Institute of Technology. And during his PhD, where he is supervised by Bernd Schiele and co-supervised by Matthias Hein, he completed several internships at Microsoft, Fusion, Hyundai, and also DeepMind. And he's currently working at the Max Planck Institute. So David, the floor is yours.
Thanks. Yeah, nice introduction. Thank you so much. Glad to be here. Before we start, one hiccup. Can you enable screen sharing again? I think we lost it in between with all the host changes. Yeah, now it works. Perfect. Okay, I guess you can see the screen. If not, just interrupt me. So yeah, thanks again for the introduction. I'm very happy to be here to talk about our ICCV paper on relating adversarially robust generalization to flat minima. And as already introduced, this is kind of joint work with my two advisors, Matthias Hein and Bernd Schiele. So this will be a short outline of the talk. As already introduced, if you have questions in between, if you are not following, if something's unclear, interrupt me. I'll try to monitor the chat. If not, I think somebody will let me know if I overlook raised hands. I'll start with a short background. I'll assume that many of you might be familiar with adversarial examples and adversarial training, but I'll just go over it to be sure and also to introduce a bit of notation. I'll then take a step back, talk a bit about the motivation and kind of the historical background of this work, so where we came from, what motivated this work, before actually introducing how we measure robustness, how we measure flatness in the robust loss landscape, and then showing empirical results of what or how this helps us to improve robustness going forward. Okay, so let's start with a short background on adversarial examples and training. So in this talk, I'll assume adversarial examples to be imperceptibly perturbed images causing misclassification, as illustrated here using this famous example from the Goodfellow paper. So these can usually be obtained simply by maximizing the cross entropy loss. So here L is the cross entropy loss, F is our classifier, X an input, delta is kind of this adversarial noise that is displayed here, and Y is the true label of the input. And usually to keep these adversarial examples imperceptible, we assume that kind of this perturbation delta is constrained by some norm, for example, an LP norm. And for the remainder of the talk, I'll always talk about L-infinity constrained adversarial examples. So this equation here basically estimates the worst case cross entropy loss under L-infinity perturbed inputs. And I'll refer in the following to this as the robust loss. And this will be at the core of our analysis, because we will look at how this robust loss changes if we now have slight perturbations in the weight space. So if we take small steps away from the minimum that we found after training. And in practice, you can imagine this to be computed using projected gradient descent, right? So multiple iterations, multiple restarts with random initializations, and then taking the worst case of these restarts. So in order to obtain robustness against these imperceptible adversarial examples, among a lot of different directions, I'll focus on adversarial training, which basically means that we train on adversarial examples that are generated on the fly during training. And this can be understood as a min-max optimization problem, as displayed here, right? So we have in the inner maximization problem is essentially our worst case robust loss. And then during training, we try to minimize this worst case robust loss to find our weights. It's good to keep in mind that this essentially means that we want the model to correctly classify not only the clean examples X, but also any potentially adversarial example subject to the L-infinity constraint. And we want the classifier to do so with very high confidence, right? So we are essentially enforcing high confidence on the L-infinity ball of size epsilon. And this is illustrated below here in this figure from the MART paper, where instead of classifying only the solid dots correctly, we now require the model to correctly classify these squares around the dots. So as I said, there are kind of a lot of different directions of improving robustness, but I think adversarial training, maybe besides certified and verified robustness, I think adversarial training is probably the most promising and also the most prominent approach in the literature, at least if we talk about empirically improving robustness. And therefore, there are kind of a lot of different variants. So you can see in this plot here on the timeline from 2018 to 2020, Goval et al. Kind of benchmark different models, all these dots. Since 2020, of course, there have been even more variants of adversarial training. But one of the problems is that the underlying factors or kind of the methods that really help to improve robustness of adversarial training are largely unclear. There are, of course, exceptions, one of which is shown here, that with additional data, so if we have access to additional unlabeled data, this generally improves robustness across the board. But you can also see that all these blue dots, they all have different variants of adversarial training, and it's very unclear which methods improve robustness and why they do so. Then there is another recent problem of adversarial training, namely robust overfitting, and this is illustrated here. So what I show here is the test and training robust loss throughout training. So the epochs are normalized. You can see that initially in dark blue, the test robust loss decreases until it starts to increase significantly again around 40% of the epochs. So this is usually after the first learning rate drop. And this is in contrast to the robust loss on training examples in light blue, which continuously decreases and converges to zero eventually, right? And this phenomenon is called robust overfitting. And just to illustrate that this is not purely a problem of very high robust loss on incorrectly classified examples, I also show the test robust loss on correctly classified examples here in pink, and you can see that we still have this robust overfitting phenomenon. Obviously, this directly translates to very poor robustness at test time. So on the right, I don't show the robust loss, but the robust test error. This is measured using auto attack, which by now I think is one of the standard benchmark attacks to use. And you can see that again, after roughly 40% of the epochs, the robust test error starts to increase significantly, ending up at the difference of a bit more than 8% between the best epoch and the last epoch. And this plot, so the red line, also shows that one of the go-to or the default solution to this problem is just to employ early stopping. Okay, so this was a bit of background and introduction of notation. And now I want to take a step back and talk a bit about where we were coming from and what insights motivated this work. And here I want to talk about weight clipping and robustness in the weight space. So before we were looking at robustness in the weight space, which is not to be confused with adversarial example robustness. So here we basically try to find out how robust models are if we perturb the weights very slightly. And we found that a very simple mechanism, a very simple regularizer, can be used to improve robustness in the weight space. And this is weight clipping. Weight clipping essentially limits the weights to a range minus W max during training, where W max is a hyperparameter. And in practice, this is just done by, for example, back projecting the weights to this range after each iteration. And surprisingly, weight clipping helps against a lot of different weight perturbations. So here I'm solely talking about random weight perturbations. So these are not adversarial ones, but just random noise on the weights. And while we originally looked at random bit errors in quantized weights, weight clipping actually also works very well against L infinity, L2, L1 perturbations, and so on. So what I show here is robustness against L infinity perturbations in the weights. And note that on the x-axis, we have this in relative terms, right? So the strength of the L infinity perturbation is reported relative to the overall L infinity norm of the weights. And on the y-axis, again, we have the robust test error. You can see that the normally trained model, so the wet one, has a robust test error of nearly 90% for very small perturbations. Note that because we have random weight perturbations, 90% corresponds to a random classifier here on Cypher 10 because we have 10 classes. You can see that as soon as we have employ weight clipping during training, we can improve robustness significantly. So for the orange curve, we have low test error for significantly larger L infinity weight perturbations. So now you might ask, why did I do this detour? Why talk about weight robustness? Well, we found out that if we apply weight clipping together with adversarial training, we can actually avoid robust overfitting to a large extent, right? So on the left, again, you see the robust overfitting phenomenon. We have this steep increase in the test robust loss during training. We end up at a very high robust test error of 62%. And as soon as we use weight clipping, in this case, with a very small W max, so this is a ResNet 18, I find it quite amazing that you can train a ResNet 18 with weights constrained to minus 0.005 and 0.005. But as soon as you do this, you see that we don't have overfitting. And because we have this large variance in the first few epochs, you can think about that as being an effect of regularization, right? So weight clipping is just a very strong regularizer that avoids robust overfitting. And at the same time, you also see in the light blue curve that we don't converge to a robust training loss of 0, right? So the gap between test and training robust loss is also significantly smaller. So why is that relevant? Well, if we think about what rate robustness actually quantifies, then we can interpret it as flatness, right? So if we talk about a model as being robust against weight perturbations, we mean that the expected loss on the left subject to a weight perturbation is very close to the original loss without weight perturbation, right? And if you were to visualize this, so Keska et al. Actually have a very nice plot for this. You can see on the left that this corresponds to a flat minimum, because now if we apply very small weight perturbations around this minimum indicated by the dot here, we have only a very small change in the loss, right? So weight robustness essentially quantifies flatness. And this brings us to kind of the main part, about kind of using this insight to actually measure this type of flatness in the robust case, so for the robust loss, and also talking about kind of our contributions and main insights. So the hypothesis here is that by finding flat minima in the robust loss landscape, we can actually improve robustness, right? So I already indicated that we might be able to avoid robust overfitting, and if you avoid robust overfitting, we usually also improve robust generalization. And the main intuition I try to depict here as follows. You can imagine that the robust loss landscape, so the loss surface, on training examples in black and on test examples in red do not necessarily match perfectly, right? So the minimum we find in the black curve on training examples might not coincide with the minimum that we find for the red curve, right? And the idea is that the flatter this black or the red curves are, the smaller the change in loss is, so the smaller the increase in loss on test examples will be, which directly translates to a smaller robust generalization gap. And ideally, this means that at test time, we have better robustness. And this is not necessarily kind of a new idea. For clean generalization, so if we don't talk about adversarial examples, just clean generalization, this idea has been kind of studied in a couple of papers already. So they are both theoretically motivated papers as well as empirical measures. One of examples is shown here, where in this paper, they tried just to visualize the loss surface. And for example, they found out that skip connections in our ResNets are important mainly because they result in a way smoother loss surface, and also optimization finds flatter minima, right? And our goal is essentially to try and elevate that to the robust case. So talking about flatness in the robust loss surface. The main obstacle here, of course, is that we all know that behavior on clean examples and behavior on adversarial examples can be radically different, right? And to this end, we essentially introduce a couple of scale-invariant flatness measure that we can use to measure flatness of the robust loss surface. And then I'll show quite extensive empirical results that try to relate robustness to finding flat minima. Okay, before talking about an objective measure, let me kind of try to highlight why we actually need an objective measure. So what a lot of papers do still to this date, so there are actually a couple of vision transformer papers that also argue that they work better because they find flatter minima, and usually this claim is supported by visualization, right? So as I showed before, people try to visualize the loss landscape in specific random directions of the weight space, right? And this is what I try to do here for several adversarial training variants. So we have a baseline at the top, but we also have methods such as MART, trace, AT-AWP, or just simple label smoothing. You see that these models achieve different robust test errors against auto attack. And on the right, I basically plot the robust loss surface in a particular random direction. And you see that most of these curves actually look pretty flat, in my opinion. But more importantly, you see that the heights of the curves are different, right? So the curves are vertically shifted, which is natural to expect because the models have different robustness, right? So they have different robust loss on the test examples to start with, right? But this makes it difficult to actually compare which model, which method looks the flattest, right? So for example, the light green one looks pretty flat in my opinion, but it's not really clear kind of how much flatness we really want to have. Moreover, this is only one direction, and we work with models that have millions of parameters. So we would have to look at a lot of different directions in order to get a good picture of which method actually looks or found a flatter minimum than others. And this is the main reason why we actually wanted to have an objective measure instead of just basing our conclusions on visualization. So in the following, I'll briefly introduce how we can measure flatness in practice. And again, we start by looking at the robust loss surface. And first, we just measure the robust loss without weight perturbation, right? So we just measure the robust loss of the model we obtained after training. This will be our kind of reference robust loss. And you can imagine if I go back, this is basically the robust loss at 0 here, right? So this is kind of the height of the loss surface. In the next step, we decide on a weight perturbation. In this case, we can take a random weight perturbation. And for this, we obviously need to decide on how large this weight perturbation should be, right? So in our case, we decide on a local neighborhood B, which I will talk about in detail later, and sample a random weight perturbation from this neighborhood, right? So this neighborhood can be understood as our epsilon ball in weight space. And then we measure the robust loss at the perturbed weights, right? So now we have two measurements, once with the perturbed weights, once without, and then we define the flatness just to be the difference, right? So we take the perturbed robust loss, L tilde, and we subtract the reference robust loss. So more formally, this can be written as follows. We have on the left-hand side, we have the robust loss with weight perturbations. So here you see that we have this expectation over weight perturbations sampled from our neighborhood B. And we subtract the reference loss, right? So note that the maximum in both cases is just the computation of the robust loss, right? So the worst case cross entropy loss. In practice, as I said before, this maximum can be computed using PGD, using a couple of iterations, potentially a couple of restarts. And the expectation is just approximated using samples, right? So in the end, we have several samples of weight perturbations. Okay, before I go on, so one important thing to note is that this measure essentially quantifies the change in robust loss. So the higher the change, the higher this measure, the sharper our minimum is, and the lower, the smaller the change is, right? So if we have a flatness of close to 0, this means that we have found a very flat minimum. So now what remains to be defined is kind of this neighborhood B that I'm talking about all the time. And we decided on a scale invariant neighborhood. I'll talk about the scale invariance on the next slide. Essentially, we treat each layer of the neural network independently. So in fact, we actually treat in each layer the biases and the weights independently, because usually biases and weights have very different distributions. And for each of these tensors, we allow a weight perturbation that is of size relative to the original norm of the weights. So let's say we have a convolutional layer, so L could be equal to 1, the first layer. These are the weights. We compute the L2 norm of the weights, and then we allow a perturbation that is, for example, 5% or 0.5% of this L2 norm. And we do this for each layer, and this is basically our epsilon ball, or in my notation, the Xi ball around the weights. So why is scale invariance actually important? Well, if we look at the loss landscape, so let's take the example on the left, the minimum that we found actually looks quite flat, right? The problem is that most models that we work with, so be it multi-layer perceptrons, be it ResNets, be it other types of ReLU networks or convolutional networks, usually have invariances in their weights, right? In the simplest case, in a ReLU network, we can usually scale weights in a specific way without changing the output, right? So we can increase weights of a particular layer or decrease them without changing the output of the layer. What that does is illustrated on the right. So if we were to scale the rates intelligently, we could make the same minimum look significantly sharper, right? The problem here is, of course, that the visualization is still on the same scale, while the weights might have been reduced in scale significantly. So we need our neighborhood B to adapt to this scaling, right? And this is essentially what we do by just allowing a neighbor, or by adapting the neighborhood essentially per layer to scale with the norm of the weights of this particular layer. And just to empirically verify this, this is a simple experiment just to see that we actually have scale invariance. So on the left, I show a visualization. So I forgot the colors for the legend, but we have in light blue our adversarial training baseline, and then the other two colors are essentially scaled models. One is scaled down by 1/2, one is scaled up by factor 2. And how we do this for ResNets is simply by scaling the convolutional layers up or down. Because most of the convolutional layers are followed by a batch normalization layer, this scaling has no effect on the output. You can see that all of these models obtain the exact same robust test error of 61% in the end. And you also see that not only the visualization is very close together, but also the robust flatness, as we measure it using the measure I just introduced, is very close together. The differences, of course, here as well as in the visualization are mostly due to randomness in computing the adversarial examples, in computing the random weight perturbations. Okay, one final note. So I already talked about visualization that a lot of papers use to justify the working of a particular method. Another popular argument is based on Hessian eigenvalues. So I compute the Hessian eigenvalues of our model, and the lower kind of the eigenvalues, the flatter I assume my minimum is. The problem is that the Hessian eigenvalues are usually not scale invariant, right? So for each network, I can just scale the network in a particular manner and get arbitrarily high Hessian eigenvalues. So this is something to keep an eye on when you read these papers, that this comparison is not always fair and not always meaningful, especially if you compare across models that have weights of particularly different scale. And just as a simple example, we all train with weight decay. As soon as you increase your weight decay a bit, you usually end up with significantly smaller weights, because that's what weight decay does. And so as soon as you have a slight change in hyperparameters, be it kind of learning rate or weight decay or something, you usually end up with different weight scales. Okay, so far so good for how we measure flatness, and maybe also a bit of what to look out for or how not to judge flatness. So in the following, I want to show results, and I want to first focus on flatness throughout training, right? So here again, we have the plot as before. The dark blue line shows the test robust loss, which you see overfits severely here. And in light blue, we have the training robust loss. And additionally, now in red, I plot the robust flatness as I just introduced it. You can see that initially it's very low. So we are always kind of walking around in very flat, around very flat minima, or in very flat basins of minima. But as soon as we start overfitting, this is kind of around 40% of the epochs, the flatness increases significantly, which means that throughout robust overfitting or during robust overfitting, we converge to sharper and sharper minima, right? And this indicates a bit that the loss in robustness that we experience because of robust overfitting might just be a result of converging to a sharper minima. And this can be confirmed just by changing the visualization a bit, right? And this is kind of a plot that I will use a lot throughout the remainder of the talk. We have on the y-axis the test robust loss, and on the x-axis we have the flatness as I just introduced it. And here I show basically how these two metrics evolve during training. We have in dark blue the early epochs, and in dark red the later epochs. You can see that we start in this dark blue point here. We improve robust loss a bit through our training, but as before, around epoch 60 or so, we start overfitting severely, and you can see that not only the test robust loss goes up, but also flatness gets worse, right? So we find sharper minima. You can see that this this relationship here is nearly linear, right? So robust overfitting goes hand in hand with converging to sharper minima. And this can be confirmed using a lot of different approaches, where we kind of see robust overfitting. But more importantly, if we have models that can avoid or at least reduce robust overfitting, we see something completely different. And this is what I want to illustrate here for adversarial training with label noise, which is just a very simple regularizer, as well as AT-AWP and adversarial training with additional unlabeled data. You see that all of these approaches reduce or avoid robust overfitting completely, right? So the robust test loss does not increase or not increase significantly in the later red epochs here. And you can see that at the same time, flatness also stays very low, right, compared to the adversarial training baseline. And this is also directly reflected in the robustness that we can measure after training, right? So with robust overfitting, we have a very high robust test error of 62%. And then the better we avoid robust overfitting, the lower our robust test error gets. Okay, so the next step would obviously be kind of going beyond a single model, right? So if I go back here, we always compare flatness within a single model. This makes sense because a model kind of lives on the same scale in terms of weights. So scale invariance is not that important, and also hyperparameters and so on are the same. So the question is, can we extrapolate that to a comparison between models? And as an intermediate step here, I have the same plot, but looking at different hyperparameters of specific methods. So on the right in the legend, you can see we have adversarial training with weight decay of different strength. We have adversarial training with self-supervision. We have traits and AT-AWP, and all of these methods for different hyperparameters. And what you can see is that those hyperparameters that perform better in terms of robustness, so that achieve lower test robust loss, also find flatter minima. And in fact, if you just draw regression lines through these points, you can see that in all of these cases, we have a clear relationship between flatness and the robust loss. So next, I want to talk about extrapolating that beyond models and actually having kind of a larger scale comparison that directly relates flatness to robustness. And I'll start with basically the core result, the core plot of our paper, which is a very comprehensive comparison of a lot of different adversarial training methods different activation functions down here. You can see popular methods such as AT-AWP, MART, traits, and so on. We have different optimizers such as entropy SGD, different learning rate schedules, different regularizers, and so on. So kind of a lot of popular adversarial training methods, as well as a lot of kind of tricks that people commonly use to avoid robust overfitting or to train robust models. And for all of these methods, we again plot the test robust loss against flatness. And you see all the gray dots that are not in a legend are essentially models that I either didn't explicitly highlight here or correspond to models of different hyperparameters, right? So as before, for each of these methods, we have a lot of different hyperparameters. And before talking about individual models, I want to highlight, if we just compute the correlation here, we have a very high correlation of 0.85. And you can see also by the regression line here that there is, on average, a very clear relationship between flatness and robust loss, right? If we now pick some specific methods, let's, for example, look at methods that we know perform very well. So methods that we know improve robustness. So we can, for example, look at traits. This is the dark brown ball down here. We can also look at AT-AWP, that's the blue diamond here. So these methods are all clustered on the lower left here, which means that they not only improve robust loss, but they also find flatter minima. However, the argument also goes the other way around, right? So we can look at methods that we know that optimize flatness. So for example, weight clipping, which is the rose dot, or entropy SGD, which is the yellow dot. These also lie on a lower left corner. So we know that if we have a method that optimizes for flatness and we combine it with adversarial training, then we also improve robustness at test time, right? So we kind of learned both of these directions from this plot. Okay, so in the following, I want to kind of break this result down a bit. And first, I want to start to look at the robust generalization gap. So instead of just reporting the test robust loss here on the y-axis, I'm reporting the difference between the test and the training robust loss. If you remember back to the plot with weight clipping and adversarial training, you saw that we can avoid robust overfitting. However, the training robust loss also doesn't converge to zero. So we had a smaller robust generalization gap. And this is also confirmed in this plot. Again, we have a clear correlation here as indicated using the red regression line. But you can also see that all the methods that perform perform very well in terms of robust generalization gap, so where kind of the difference between test and training robustness is very low, also find flatter minima. On the right, we have a very similar plot, which explicitly quantifies the effect of early stopping or of robust overfitting by quantifying the test robust loss, the difference between the last and the best epoch. If we have a lot of robust overfitting, this difference is generally high. If we can avoid robust overfitting altogether, this will be very close to zero. And you think that you see that there are actually a lot of methods that are close to zero, so that have no or very small robust overfitting. And again, you can see that these methods also find very flat minima, while those methods up here that have severe robust overfitting also converge to sharper minima, right? So this basically shows that the insights we had before by looking at one model also generalize to kind of all these different models that we looked at. This last point, I just want to make this very explicit, that what early stopping essentially does is early stopping essentially optimizes flatness, right? And this is shown here. We have for a few methods where we have severe robust overfitting. I show basically the difference between the last and the best epoch, right? So without early stopping and with early stopping, and both of the dots are always connected by the lines. And you can see that in all cases, early stopping not only leads to a better test robust loss, but also to a flatter minima. Lastly, I briefly want to highlight that all the plots I had before were computed on test examples, right? So both the robust loss, so the y-axis, was computed on test examples, as well as the flatness was computed on test examples. So you might interject that this is kind of not really helpful in practice to, for example, select models, to select hyperparameters, and so on. So here we just validate that our observations also hold if we compute the flatness on the training examples, right? So the only difference is the x-axis, where we now compute flatness on training examples. And even though I didn't draw the regression line here, you can again see that there is a very clear correlation. Methods that we know that work very well also have a very good flatness on the training examples. Okay, so these were kind of the main results, and before I want to summarize and conclude, I briefly want to talk about an alternative way of measuring robust flatness that we also considered in the paper, but that had some problems, and this might just be a reason to continue this line of work and investigate why some measures don't work as well as others. And this is specifically an adversarial robust flatness measure. So if you look at the lower part here, the only thing that changes, highlighted in red, is that we don't have an expectation here, but we have a maximum here, right? So instead of considering random weight perturbations, we now consider particularly bad, particularly adversarial weight directions. And in practice, we can do this by jointly optimizing adversarial examples and the adversarial weight direction for the left part, and then the reference robust loss on the right stays the same anyway, right? So the only difference, so you can imagine the main difference is that we move from an average case perspective to a worst case perspective, right? So above, I plot how this looks for our adversarial training baseline. Same plot as before. You can see in red the average case flatness that I introduced before and how it increases as soon as we start overfitting. And now we have in yellow also this worst case notion of flatness. And you can see that this generally is a bit more sensitive. You can see that in the beginning, there's actually a decrease, right? We in the beginning where we kind of in the beginning of learning. And you can also see that as soon as we start overfitting, the increase is much more significant. Of course, the altitude here also depends on the size of the neighborhood, but generally the worst case notion is a bit more more sensitive. But the insight is essentially the same. If we have robust overfitting and independent of how we measure flatness, we converge to sharper minima. And this can also be seen here if we just compare the average flatness and worst case flatness side by side in this plot as before. You can see on the left the same plot that we had before, and on the right with worst case flatness it looks very similar. As I said, it's a bit more sensitive. You can see that after the first epoch in dark blue here, flatness actually reduces a bit, but then as soon as we start overfitting, it goes up. The main difference, of course, is the scale that worst case adversarial weights are usually lead to higher robust loss change in general. Okay. So the problem with that is that if we now look at the correlation between the robust loss and worst case flatness across methods, the story is not as clear anymore as before, right? So you can see the correlation is only 0.54, so there is still a correlation, but you can see especially on the lower right corner here that there are a couple of outliers. Interestingly, the blue outlier here is AT-AWP, so adversarial training with adversarial weight perturbations, which should ideally optimize this worst case notion of flatness during training. Of course, there are slight differences between how they implemented it and our worst case flatness measure, but it's still interesting that AT-AWP in particular is an outlier here. Some of the gray dots here also belong to AT-AWP with different hyperparameters, right? So you can say if we factor this out, we would have a stronger correlation, but this also indicates that kind of this worst case notion of flatness is not entirely or not as conclusive as the average case before. And we suspect that a main problem with this worst case notion is that optimization or the flatness measure is much more sensitive to the optimization hyperparameters. And we use, so to compute the flatness for all these methods, we use the same hyperparameters. And I imagine that this might not be ideal because the loss surface, depending on the scale of the weights and so on, the loss surface might be very different locally around the minima for these different methods and might require different hyperparameters to compute the worst case flatness. So this definitely leaves some room for improvement or for future work here to see how we could appropriately compute this worst case notion of flatness. Okay, so this is all for the results, and I briefly want to summarize, and then of course I'm happy to answer any questions and discuss with anyone interested. So the main contributions of our paper are kind of twofold, right? We have these kind of two measures of flatness in the robust loss landscape, right? And then the two main insights from the empirical results are first that robust overfitting and flatness are very closely related, right? So I showed that robust overfitting leads to sharper minima. Vice versa, you can also say that if we converge to sharper minima, we also overfit, right? And this kind of tells us a lot about how we can potentially avoid robust overfitting. And this also tells us that a lot of methods, a lot of regularizers that we know avoid robust overfitting do so by avoiding sharp minima, right? So by kind of favoring flat minima throughout optimization. And second, I showed that this also generalizes across the model. So not only comparing one model across epochs, but also comparing the final models across a lot of different adversarial training variants and regularizers and activation functions and so on, some of which are again shown here. And essentially the main insight is that there is, across all these methods, a strong correlation between flatness and robustness. Again, this tells us two things. This tells us that a lot of the popular methods we use every day are more robust or improve robustness by at least partly improving flatness. And this also tells us that if we develop new methods that improve flatness or that kind of optimize flatness during training, we can apply it on top of adversarial training and potentially also improve test robustness. Yeah, so if you're interested, the paper and everything, and also the code with a couple of examples of how you can easily compute these two flatness measures for your favorite models can be found on my webpage. And yeah, I'm a bit earlier, but I'm happy to answer any questions and take comments and so on. So I already see a couple of hands raised. Not sure if somebody has to unmute people.
Hey, can you hear me?
Ah, yeah, perfect.
So first of all, thank you for the great talk. I really, really enjoyed it.
Yeah, thanks.
I had, basically, when you compute the difference between the two losses, right? I mean, the terms, you average among like some sampled random direction, right?
Yeah.
So it means that, I mean, how does this scale with the number of direction you sample? Because I imagine that the more you get, the better the estimation is. But what's happening if, I mean, you want to do something like super local and you want just to sample one direction, and in this case, what happens? So how this measure changes?
So essentially, I think we don't have very large scale experiments in the paper or the appendix, but I recently did some, so I can give you a bit of an intuition. So essentially, so there's I think is one important factor is the standard deviation, right? So essentially asking how many samples do we need to have a reliable estimate? And I think in the paper, we only use 10. The main reason for that is that if we go above 10, it just gets computationally more expensive, but we don't really get kind of a clearer message or clearer results. And with 10, the standard deviation is already pretty low, right? And the other thing is a bit talking about the extremes. And this is a good case, right? So you can have, if you sample random directions, you can have quite a bit of variation in terms of kind of picking a particularly bad one or a particularly good one. But I think we initially tried it for like multiple thousands, if not 10,000s of directions. And we basically never saw kind of these extreme cases that you would usually compute using the worst case measure, right? So of course you have a bit of spread there. That's why you need kind of a minimum number of samples. But if you compute more than like 10 or 50, the story kind of is very similar, at least if you average, right? If you, of course, take the maximum here, then you need a lot of samples in order to really compute the maximum using sampling. And that's why we, for the worst case measure, used a gradient approach.
So just, I mean, so on top of this, so basically, is it possible like you choose just one X, just one, because you want instead of, I mean, the curiosity that basically raised with the answer was like, okay, what if I don't want like a global estimation, but I want like, you know, local, like in that single point. So it's I just fix X and I just search with V. Is that correct?
Yeah, that's a good question. Sorry, then I misunderstood you.
No. So follow up.
Yeah. Okay. Perfect. So that's a good question. So what we did, and so all the results I showed There we computed so if I have, for example, kind of this main plot here, I computed test robust loss on, I think, 1,000, the first 1,000 test examples on Cypher 10. And for the flatness, I do the same, right? So if we go back to the equation, there's obviously kind of an expectation or kind of a sum there that goes over kind of 1,000 test examples.
Okay,
so we didn't actually try to do it very locally. So we didn't try to do it for 1x, for example.
Okay.
I think we did initially experiments because it's computed batch-wise, right? So initially we tried just one batch of 100 examples, and in the end we did it then for 10 batches with 1,000 examples. Okay. We didn't see a significant difference between 100 and 1,000 examples. Okay. But I would guess that there is quite a bit difference between and only using one example. I think that the important assumption that I remember debugging something like that initially. An important thing is if you need. So with 100 examples, if you have a balanced data set, it's very likely that you have 10 classes, 10 examples of all the 10 classes, right?
Okay.
But if you have one example or you have 10 examples of only the same class, then if you think it a bit about in an adversarial way, it's very easy to find a random direction that has no effect, right? Because you only need to keep one class constant. So you can, if you think about an adversarial way, if you are only interested in one example, you can find an adversarial direction which makes the classifier constant, but you don't notice because the constant classifier predicts the class that you are just looking at, right? So I would expect there to be a difference if you look at very few examples.
Okay, thank you, really thank you.
Yeah, I think Batista and Katrin, I'm not sure who wants to go first.
Okay, hi David, thanks for your talk. I think I can go first. It's just a curiosity that I have. So I've seen this recent trend, which I don't know if you share with me, that the latest models exhibiting, let's say, higher robustness, those especially from DeepMind, seem to be larger, so that they go for larger models and they train with more data and more adversarial retraining rounds. So do you think there is any connection here with your work? So maybe larger models, in a sense, have larger flatness, and then you can avoid robust overfitting, and that's why they can train with more adversarial examples? Or, I mean, is there any kind of, because there is, on the other way, there is a trend in saying if your function is overly complex, then your model is strongly overparameterized, and maybe it's more vulnerable. So what's your feeling here in terms, so what is the connection between, let's say, robust flatness and the size of models in general?
Yeah, that's a very good question. So we didn't explicitly, so all the experiments I showed were ResNet 18, so we didn't really do a lot of experiments with different models. In the paper, you will find experiments with a couple of wide ResNets. These do indeed look flatter, but these were also pre-trained models, so from different papers. So I expect that these models are already kind of highly optimized in terms of hyperparameters and early stopping and so on. So it's kind of hard to analyze them if you don't have the history of epochs. So that's one thing. Generally, I expect that with larger models, you of course have a larger chance of overfitting, but especially the DeepMind models, of course, especially if you train with unlabeled data, then of course that's very strong regularization, right? That's what I also try to, or that's what we also saw, right? So just using more data, so it doesn't have to be unlabeled, just if you have more labeled data, for example, or pseudo-labeled data or whatever. This is already very strong in terms of regularization and also improves your flatness in general. And I would expect that if you have too big of models and you don't have any regularization in terms of additional data or something like that, or AT-AWP or whatever, then you have a higher chance of severely overfitting. But I think, I mean, from how I understand is, in particular, the DeepMind papers, they usually have kind of, they don't just do adversarial training, they have kind of a longer series of methods and regularizers that they put on top. And I think you really need that to kind of get good robustness, kind of get better robustness with kind of these deep models, right? Or the larger models. Yeah, I hope that answered a bit. But
but okay, so you don't have a strong preference, let's say, in going for larger models or smaller models?
I don't have a large preference there. I would expect that smaller models generally have less of a incentive to overfit because they just have less complexity to allow overfitting, right? So I would also expect that if they have less overfitting, they converge to flatter minima. But on the other hand, we also know that if you regularize the big models very well, you can kind of improve robustness even further, right? So I think it's a split sword there a bit. So yeah, I mean, from as I said, we didn't try these really. I think the DeepMind paper, they have wide ResNets 70 something by now, right? I'm not sure if I would be able to train those. But I think for these models, it would be very hard without any unlabeled data or without any regularization to avoid overfitting, right?
Okay, thanks.
Yeah. Okay, I think Katrin also.
Yeah. Let me thank you as well for this great talk.
Yeah.
And I'm actually forwarding a question from YouTube from Tim von Hammer.
Okay,
I'm sorry
cool.
if I mispronounced his name. And he's asking if you repeat the experiments for other problems besides Cypher 10, and if the trend is equally clear and flatness as easy to measure for more complex use cases.
Yeah, that's a good question. So we don't have any other results than Cypher 10 in the paper. We had some initial papers on SVHN and MNIST that we didn't include in the papers, where it looked very similar, but of course MNIST and SVHN are even simpler, right? So it's not, I guess, not really a good answer to that. So it would be interesting to see how this goes for larger models. I think in adversarial robustness context, the next best thing would be Cypher 100, because ImageNet is kind of still a threshold for adversarial training. And then can you say the second part again?
Whether the trend is equally clear and flatness is easy to measure.
Okay, yeah, I think I answered that. So on the easier data sets, flatness tends to be easier to measure, but this also might relate to the fact that you use kind of smaller models and the kind of loss surface might be less complex. What I wanted to say in this regard is, so we didn't too much focus on different data sets. What we did, but what didn't make it into the paper before the deadline, is that we have similar experiments actually also for L2 adversarial examples. So from that perspective, I would expect it to generalize at least to Cypher 100 and similar data sets. But yeah, if you want to have proof of that, it probably would take a while for somebody to do the experiments or for me to do the experiments. And for ImageNet, I don't have super intuition about how this would factor out on ImageNet, but there was this recent sharpness-aware minimization paper also used for vision transformers. And these are, of course, experiments on ImageNet. This is not in terms of robustness, right? So they don't look at robust flatness, they just look at flatness and cleanness. And there it seems still to make sense, right? They have, of course, slightly different measures, and it's not about large-scale study, it's more about individual models. But judging from that, I would expect it generalizes, but I think the main obstacle is having kind of a large zoo of adversarially trained models on ImageNet, which we currently don't really have, right? Yeah.
Since there is no other question, Tim also had a second question, which is, why is it important to obtain adversarially robust systems? Is it mainly for security reasons or are there other reasons?
Yeah, that's a good question. There are probably people in the audience that can answer that way better than me. Maybe somebody else, but this also wants to chime in. But yeah, I mean, for me, there are always two reasons. There's, of course, the security reason, which I think is important, especially if we talk about kind of security critical applications. Of course, these L-infinity adversarial examples are not super important in all of applications. In some applications, it might more be about very specific distribution shifts, like in the medical domain, but these can also be adversarial to some extent. In autonomous driving or something, it might more be about adversarial transformations or corruptions or something like that. But this brings me to the second part, and the second part is essentially trying to understand deep learning, right? I mean, adversarial examples, especially these L-infinity or LP constrained ones, are just easy to study, and they allow us to kind of find a lot of interesting phenomena and kind of try to kind of understand where models fail. And I think recently, let's say the last 1 or 2 years, there were really a lot of papers that try to translate these insights to, I mean, there were papers about using adversarial examples for privacy, using adversarial examples for improving image recognition and stuff like that, right? So I think personally, I find it most exciting for understanding deep learning. and the security aspect for me comes second. But of course, if for a lot of applications, the security aspect might come first, and understanding aspect is more like my personal hobby or something like that.
Okay.
Okay. I'm not sure. I don't see any hands.
Okay.
I don't see any other questions. I mean, I leave another minute to the audience to ask additional questions. Maybe I can squeeze in a question.
Yeah, of course.
I wanted to know how costly it is to compute this flatness measure, and what are the factors that actually affect it most.
Yeah, I think the most expensive part. So for the average case one, the most expensive part is essentially the adversarial example computation, right? If you want to have good estimates of your robust loss, you usually run PGD, let's say, for like at least 100 iterations, and you do a couple of restarts. And I think this is the biggest chunk. If you talk about the worst case notion of flatness, then of course on top of that you have the optimization in weight space, right? And so you can check the paper. We actually discussed this a bit. How you do this, and what we ended up doing is actually doing it jointly. So you have, like, in each iteration, we compute gradients both with respect to the examples and the weights. And then, of course, you basically have, not double, because they are kind of way more weights than examples, but you have the training or the optimization complexity in both the inputs and the weights, right? So you can imagine, like, it would probably scale very similar to adversarial training, right? Where you also have the weights updates and the adversarial example computation. And then it depends a lot on the model size, obviously, right? So for the wide resonance we had, it's obviously a lot more. Even my implementation might not be ideal, but even kind of sampling random weight perturbations for like 50 million weights is kind of non-trivial. And PyTorch, or kind of a lot of these libraries, they don't really intend you to do that, right? They intend you to sample in the input space and not in the weight space. So yeah, the worst case obviously scales not that well, but the average case should be pretty straightforward. And as I said, for most of the experiments, you don't need too many samples, which is nice, because if you start, of course, with 1,000 samples or more, then it also takes quite a while. And it also, I mean, you also need to save all the stuff, so you don't want to do that.
And as a follow-up question, can you reuse something that you compute for actually improving training? Like in the case of adversarial, in the worst case, you have the adversarial examples already. So can you reuse them while training? Probably yes.
Yeah, so if you would use any of these measures during training, yeah, then you do it batch-wise, you could reuse that, right? And of course, depends a bit on how you want to do the optimization then. But yeah, similar to AT-AWP, for example, where you also can reuse the adversarial examples, right? But yeah, I guess this depends a lot on yeah, what exactly you want to optimize and so on. And there is a lot of there. So just as a reference, there was this SAM paper, so sharpness aware minimization, and I saw on ICLR also a paper on understanding sharpness aware minimization, and they actually discuss a bit of these details. If you want to do these weight perturbations during training, do you do it on batches? Do you do it on individual examples, right? This is, of course, an important question, but it also impacts a lot your complexity, right? If you do it on many batches, it's obviously less expensive than on each example or something like that.
Okay, thank you.
Yeah.
Maybe Catherine, can you confirm there's no other questions around?
Yeah, there's no more questions at YouTube here.
Okay, then
cool.
Thank you, David, for the amazing talk, and also
Yeah.
for answering all our questions that were a lot. And
yeah, thanks for having me. Pleasure to be here. Thanks for the questions. Thanks for the comments. Thanks for the organization, of course, for you.
Oh, no. Thank you for joining us, and thank you to all the audience and everyone who joined the event. So I'll now stop the live streaming. All right. And that's closing time.